So this is the last lecture for our upcoming exam. At the end of today's lecture, that's the end for exam 3. And then we'll start material for exam 4, and that will actually be a little different than the chapters in the book. We're not going to go to renal and electrolytes. We're actually going to go ahead and go to digestive. You guys are doing digestive in lab next week, and that's the pathway we're going to use. The reason we're doing that is because our old text was digestive before renal, and all of the old exams are all digestive and not renal. So you'd actually have to pull up a couple of different exams in order to actually study if we actually changed our format. So we're not going to change our format. We're just going to make the book adapt to us instead of us adapting to the book. Okay. We ended up talking last time about carbon monoxide poisoning and how it actually causes oxygen deprivation at the cellular level, and that in order to fix that, we actually have to get carbon monoxide out of our environment, treat with pure oxygen and hyperbaric pressure if needed. Carbon dioxide transportation in our bloodstream is via 3 different mechanisms, and we're starting with the least amount, and then we'll end up with the largest amount on how we carry carbon dioxide in our bloodstream. A little bit of it is dissolved in plasma. Not very much, but it's actually, carbon dioxide is actually more soluble in water than oxygen is. So we do have some of it dissolved in the plasma. The other way that carbon dioxide is transported is there is actually a binding site on hemoglobin specifically for carbon dioxide. The binding site is different than that for the binding site for oxygen. And whenever carbon dioxide is bound to hemoglobin, it has this long name that's always a tongue twister for me, carbaminohemoglobin. I always have to stop and think about it as I try to say that. So about 20% of our carbon dioxide is actually carried around on hemoglobin. And we know hemoglobin is going to go to external respiration as well as internal respiration via the bloodstream. The main source of carbon dioxide transportation, however, is as the bicarbonate ion, HCO3, with a minus charge. This is done via an enzyme that's inside our red blood cells called carbonic anhydrase. So carbonic anhydrase helps us to actually create a chemical reaction where we combine carbon dioxide and water inside our red blood cells and get carbonic acid using carbonic anhydrase. Acids are interesting little compounds in that the stronger the acid, the more it wants to disassociate. What that means is that the stronger acids will actually immediately separate into hydrogen ions or protons and the other component of that molecule. So that would be bicarbonate in this instance. However, one of the things to actually realize is I'm going to have a little beaker over here I'm going to draw with solution and another beaker next to it with solution. And in the first beaker, I'm going to dump hydrochloric acid into it. In the second beaker, I'm going to dump carbonic acid into it. What will happen is that this acid is so strong that you will not find the molecule intact. It will all be separated. So hydrochloric acid is really strong. The carbonic acid, however, we will find some protons in solution, but we will also find a lot of H2CO3 in solution. So that's what makes it a weak acid. A strong acid, lots of protons. A weak acid, not so many protons. A strong acid has a low pH, and a weak acid doesn't have as low of a pH for that. So with this reaction that we actually have over here, this is producing a weak acid, so we will find some of this inside the red blood cell, but we will also find some protons and some bicarbonate ion. What's important too is that when we are at the tissues, that's where our CO2 is the highest, correct? And so this reaction is driven in this direction. When we get to the lungs, what's important is that the reaction is driven in the opposite direction when we get to the lungs. And we want to do that because at the area of the lungs, we actually want to have carbon dioxide then released at the level of the lungs. And so this reaction goes both ways. And carbonic anhydrase can help move it. The more carbon dioxide you have, the higher the carbon dioxide level, the more it pushes it in that direction. And then the lower the carbon dioxide level, the more you will actually push it into the opposite direction. So that carbon dioxide level is really important as to which way you drive that equation. There was another guy involved in the chemistry and physics of gases, Haldane, and he decided that in his observation that if we had low PO2s, we actually noted that there was more carbon dioxide being carried in the blood and carried along with hemoglobin, because remember, hemoglobin has a carbon dioxide binding site that's separate from the oxygen binding site. So at our tissues, because we have low PO2s at our tissues, this helps carbon dioxide actually bind up and load onto hemoglobin. In other words, it's not such a crowded molecule, because if you have a bunch of oxygen, the oxygen crowds out the carbon dioxide. And so that's where at the area of the lungs, because of the high PO2, we actually have the hemoglobin actually getting rid of carbon dioxide with it too. And so Haldane noted those effects, and they made a law after him. Talking a little bit more about carbon dioxide and blood pH, I want you to realize that there is absolutely an inverse relationship between carbon dioxide levels and pHs. So what that means is the higher the carbon dioxide level, the lower the pH of the blood. And that's because if we increase CO2, that drives this reaction into the direction where we're going to produce more protons and carbonic acid. And CO2 for us has a very direct relationship to blood pH. And we can modulate that or affect that via our ventilatory rate. Let's take a look at some of the byproducts of this equation right here with the bicarbonate ion and also carbonic acid. Let's start with the bicarbonate ion first. In order to keep our pH at a certain level, we need to have in our blood various buffers, and buffers are defined as those chemicals which will minimize pH changes in the presence of various acids and alkalis. So a buffer is added to a solution in the chemistry lab to where you can actually then dump in more and more acid, and it takes a while for the pH to change. And so we have to have a lot of natural buffers in our bloodstream to help minimize pH changes, because we will produce metabolic acids, and we will also have times when we have a respiratory acidosis. So we need to minimize that. The bicarbonate ion is something that some people used to ingest on a regular basis when they had heartburn in the form of baking soda. I don't know if you know of anybody that uses baking soda to treat heartburn, but that's one of the buffering mechanisms that sometimes people use over the counter. So that what they're using is the bicarbonate ion in there. So when we use bicarbonate ion as a buffer, I want to ask you, is the solution too acidic or is the solution too basic or alkaline that we're actually utilizing it as a buffer? In other words, what can it accept? An acid is a bunch of protons, and then a base is a bunch of hydroxyl ions or very little protons in there. What's important here is this bicarbonate. If we are in a high proton environment, the bicarbonate ion will actually buffer that. So it's a buffer for excess hydrogen ions, or in other words, an acidotic situation. The acid, carbonic acid, is a buffer for the opposite. And so if we actually have an alkaline situation, we can put in some acid to a base or an alkali, and that will also help produce a buffer for us. These two things right here help us to keep our blood pH around 7.4. Let's actually use these two guys with an example of some really strong acid. So hydrochloric acid is a really strong acid. We just talked about it. It separates or disassociates into a bunch of protons right away. What of the two guys up above would we want to actually add to this solution if we had a bunch of hydrochloric acid in to help buffer it or to minimize, to actually keep the pH from going down so low? The bicarbonate. So HCO3 with a minus charge. Now, in our bloodstream, you realize the other thing that we actually have a lot of in the interstitial fluid that is a cation is some of the stuff that's in baking soda. We have a lot of sodium in our bloodstream. So you'll also have sodium bicarbonate there. So I'm going to add that on the beginning of this and therefore take away my little 3. And that's because you guys know sodium ions are floating around all the time in our bloodstream. And what that will do is then, because this is a strong acid, we would rather deal with a weak acid, and so what we'll get is H2CO3 plus NaCl, salt. So this is an example of how our bicarbonate is helping to minimize a really aggressive attempt to change our pH. Now let's take a look at a really strong base, sodium hydroxide. And so we're going to add a weak acid to a really strong base here, H2CO3, and that will help us actually come up with NaHCO3, which is sodium bicarbonate, plus good old-fashioned HOH, which we all know is also H2O. So here is a really strong base, and now we have, in essence, a much weaker base and water. And so that's what a buffer does. It takes a really strong acid and knocks down its strength to a much weaker acid. That's something that we can tolerate. And same thing that we actually have here with a really strong base. So we want to minimize our pH changes, and we do this with this methodology where we actually carry around the bulk of our carbon dioxide as that bicarbonate ion.
What happens with people with a very alkaline diet? So they eat like no meat, a lot of foods that are high in alkaline, and so what happens to their pH and their reactions to their body?
Well, people who eat an alkaline diet, the area that it's going to first come into contact is with the hydrochloric acid in your stomach, correct? And so it will have a more rapid neutralization of the hydrochloric acid in your stomach. And then that could impact the pH of the food entering into your small intestine. And that pH is supposed to be acidic, and you have other secretions actually entering into the small intestine to actually help normalize that. If you have less acidic pH in your small intestine and put in more alkali, which is what our body does, then you will not activate certain enzymes. So an alkaline diet is kind of messing up with your body's normal enzyme activation process.
So would you say it slows it down overall?
Yeah, it'll slow down some of the absorption because of inactivation of enzymes. It's the only thing I can suppose. But I will tell you, the more alkaline you put into your stomach, the more acid your stomach will make. So, and we'll get into the digestive chapter, because your stomach has receptors that actually monitor the pH, so to speak. And so if the pH isn't really low, you will actually produce more hydrochloric acid. So that's just the way it works in our body. It knows better than we do about what it's supposed to do. So control of ventilation. So what makes us actually move air? We actually have ventilatory centers in our medulla oblongata, which also has centers for other things that are basal for us, correct? Medulla oblongata controls our heart rate, controls our blood pressure, and also now we know controls our respiratory rate. So we do have the ventilatory centers there. And the main group that works there is the inspiratory group, because we have neurons in the medulla oblongata that fire like our nodal cells in our heart. So they fire spontaneously. They actually have a normal rate of firing so that you actually ventilate or actually move air. And so when they fire, nerve impulses are sent down the phrenic nerve, well, we actually have two phrenic nerves, and intercostal nerves. And so these are going to stimulate two very specific muscles. The phrenic nerve is going to stimulate the diaphragm. And what other muscles that are the intercostals going to stimulate that also helps us to expand our chest dimension? The external intercostals. So that's the inspiratory group. We do have an expiratory group. It's not actually very active, and it's typically only active during forced expiration, where we're contracting our internal intercostals, trying to actually pull down the rib cage, decreasing the dimension of the thoracic cavity via that mechanism. There are also ventilatory centers in the pons. Remember that the medulla oblongata is the base of the brainstem. After that, we get the spinal cord. Going cephalad or superiorly from the medulla oblongata is another area called the pons, which is actually just a bridge. But what's interesting, in the pons we do have a pneumotactic center and an apneustic center. One of them is active during the daytime and the other is active at night. Which one's active at night? Apneustic center. And so these are basically telling you the pons will actually tell the medulla oblongata, we're sleeping now, slow down your ventilatory rate. We're awake now, so increase your ventilatory rate. So the pneumotactic center is active during the daytime, and the apneustic center is active and talking to the medulla oblongata, so to speak, at night. Yes?
If you're unconscious, would it be the apnea?
If you're unconscious, then the apneustic center would be kind of help possibly modulating the medulla oblongata. The medulla oblongata would be firing anyway. These are centers that typically have in the pons that are going to respond to what we call a circadian rhythm, your day-night cycles. So that's typically what activates those. Not being knocked unconscious, I'm not exactly sure about that.
I see what you're saying.
Yeah.
I know it's just automatic.
Yeah. Other factors influencing the rate you actually ventilate or breathe. We have higher brain centers, the hypothalamus, so that's before the cortex, and then cortical centers. The hypothalamus is a center also that has part of our emotional brain, and so we're working on that emotional center in the hypothalamus. And so with the emotional center, we can actually laugh and cry, and those things will all change ventilatory rate. Cortically, we can think about our ventilatory rate, correct? We can decide to stop breathing, and we can decide to breathe faster. And so that's what we mean by cortical control. We actually can voluntarily control ventilatory rate. But how long can you hold your breath, realistically? Not very long, and so you will actually have the medulla oblongata stimulating your diaphragm to ventilate, even if you are actually trying not to. So you have a limited amount of voluntary control, and obviously the emotional center too will have a certain amount of, a limited amount on the control. The last factor that we're going to talk about that affects the ventilatory rate is our PCO2 level. He's the star of the show. That's the most important chemical control of ventilatory rate. And that's because the higher PCO2 means what to your pH? Lower pH. And a lower pH is bad for you. Your body knows that. And so we can actually ventilatorily adjust your carbon dioxide level to actually impact pHs. So hypercapnia and hypocapnia are all related to CO2 level. Hypercapnia means too much CO2 in the system, and hypocapnia means too little CO2 in the system. So how do we create hypercapnia? What's a way you can create hypercapnia in yourself? Hold your breath, right? Okay. How do you fix hypercapnia? Hyperventilate. So that's pretty easy. Now, hypocapnia. How do you create hypocapnia? You hyperventilate. You have to do a lot of hyperventilation to create hypocapnia. And therefore, how do you fix? Hypoventilate or breath hold. So we'll just say hypoventilate, because breath holding is a hypoventilation type of thing. And so I always found it rather interesting. I was born and raised in Anchorage, Alaska. So I was there before I was born in Alaska before it became a state, so that's how old I am. So anyway, there's a lot of strange people in Alaska. And I can say that because I was born there, and I recognize the strange people. When I was a kid on the playground, we had this one kid named Bobby, and Bobby liked to hold his breath and watch us girls freak out. Because when he held his breath, instead of him turning blue, he turned really red. And the reason he turned really red was because he was really trying really hard to keep it, holding his breath. And if he holds his breath long enough, theoretically he'll pass out. But most people can't seem to hold their breath that long to where they actually would pass out. And so they always take a big breath in. Well, I don't remember him ever trying to hyperventilate, but I know little kids will try to actually manipulate their parents. Because they have limited resources in which they can actually manipulate their parents. And so they will use themselves as a manipulative tool. And so they will try to hypoventilate or hold their breath to upset their parents, or hyperventilate to upset their parents. And either way, all you have to do as a parent is you need to just stand there and say, okay, you go ahead, go for it. I'm just going to catch you when you fall. And so if they hyperventilate, one of the things that actually happens with hyperventilation when your CO2 level drops, your brain doesn't like it. So your drop in CO2 is recognized by the brain. And this is one where you actually can pass out from, because the brain says it's like you're flushing too much CO2 out. So if you're flushing too much CO2 out, what would the brain's vessels want to do to stop flushing out all that CO2 too fast? They vasoconstrict. Absolutely. So the brain, BVs, vasoconstrict. And this vasoconstriction causes dizziness and even fainting. And so the thing about it is you have to realize if something is somebody's hyperventilating on purpose to where they actually pass out, the only thing you need to do is make sure, as I said, you catch them on the way down so they don't hurt themselves. But let me ask you, because they passed out, they no longer can be messing with their ventilatory control rate voluntarily, correct? So when will they start to breathe? Because what happened was the pH went the wrong way, correct? Okay, so the pH went up, and so they will not actually start to naturally want to ventilate. The medulla will not tell them to ventilate until the pH is starting to go down and maybe dip down a little bit below normal. So you have to realize that they may not breathe for a little bit. You still don't have to worry. You just keep an eye on their coloration and just remember your CPR. Which you won't have to do, because if they were that mentally aware where they did it on purpose, then they're fine. They're just being a little bit of a turd. What can you say? All right. So that's the story of hypercapnia and hypocapnia. And then now let's talk for just a moment about PO2. So remember, P stand for partial pressure. And we do have, remember baroreceptors in the aortic arch and the carotid sinus. They're called aortic bodies or carotid bodies. And they also can measure PO2 concentrations. The important thing about PO2 concentrations is that only impacts ventilation when the change or drop is rather extreme. And I want you to realize that when we send all of that lovely O2-rich blood out to the tissues, and it's bathing, we're bathing our tissues with that O2-rich blood. At the beginning of the capillary bed, the cells are getting the most oxygen, right? And then as we move along the capillary bed, the oxygen levels lower, and even as we're moving further along, the oxygen levels lower, but we're still getting our oxygen from our blood for our tissues. You guys following me with that? Until we finally get to the end of the capillary bed where our PO2 is 40. So what that's telling you is that the one at the head of the fountain is getting the most, and the others are getting less, but they're getting enough. You guys follow? And so this is why O2s are not very good for ventilatory control rate, because our body can actually still survive with rather low PO2s. And this is seen all the time in people with emphysema or COPD. And when people have COPD or emphysema, they're walking around all the time. If they don't have any supplemental oxygen, they're walking around all the time with low PO2s in their arterial blood and high PCO2s in their arterial blood. And so when I say low PO2s, they're in their 70s, maybe their 80s if they're lucky. And then their PCO2s are in their 40s and not 40s, but 50s. Rarely 60s, but the PCO2s are actually in their 50s. So they're running around with a high PCO2 and low PO2s in their arterial blood before it gets to the capillary bed. And when it gets bad enough, then you see them walking around with the little nasal cannula carrying their oxygen around with them, right? And so the supplementation of oxygen they're getting is actually kind of low, because the higher the oxygen content that you give them, it will actually cause their respiratory drive to go down. And so with people with COPD, they have to be very careful with oxygen supplementation, because if you give them too much oxygen, their respiratory drive goes down, and what happens to their CO2 levels? Goes up, and then their acidosis gets worse. The important thing, and I know why this book went on to renal after this, is that you have to realize COPD people, if they have a high PCO2, that means their pH should be acidotic, right? But the kidneys come in, and the kidneys will actually preferentially excrete acid in the urine, and also the kidneys will make bicarbonate to actually help to balance the acidosis for you. And so the kidneys are a long-term regulatory control organ for chemical imbalances that are non-lethal and occur slowly over time, because people who get emphysema, they don't get it overnight. It is a process that occurs slowly over time. Unlike a metabolic acidosis, which you see with diabetic ketoacidosis. Diabetic ketoacidosis is a process that was smoldering and then suddenly ran away. And with DKA, or diabetic ketoacidosis, that's a metabolic acidosis. And what do you know the person's body is going to do first, because it has the ability to do this right away, to help try and actually raise that pH. What are you going to try and do to up your pH if you have diabetic ketoacidosis? You will blow off your CO2. So the ventilatory rate for people with DKA is actually pretty high, but they're still acidotic, because even though they're blowing off all the CO2 to raise their pH, if they're still acidotic, that means that the kidneys are not able to actually kick in rapidly enough to compensate, and so that's why medical intervention is necessary. So that's the end of the story, and this is the end of our information. So exam 3. And remember, when we get together on Monday next week, it will be the digestive chapter that we'll be starting on. You guys have any questions? Yes.
I was just wondering, so like when you take someone's oxygen, it's a percentage, like 98 or, you know, however high.
When you use that little pulse oximeter on their finger, yeah.
So I'm just, how does that correlate with the reading of the levels, like either 104 or like?
So the pulse oximeter is using some a chromatophilic type of process to actually ascertain how much oxygen saturation is occurring in your oxygenated blood.
Okay. So, like
So
if
you're
98 it would be like the highest that it should be.
If you were-
at the fingertip.
Yeah, if you were at 98 to 100%, that means your PO2 is around 104.
It's curious because it's reading at the fingertips, so that's far away.
But remember, where does the actual cellular respiration occur?
In the cell.
In the cells. And when do we get to feed our cells from the bloodstream? At the capillary bed. So yeah, you're still in, it's still measuring arterial blood is what it's measuring. And it's not into the capillary beds that you're actually measuring that. Yep.
Is
Okay.
that why they're always tired?
The COPDers?
Yeah, because at the physical therapy clinic I work at, a lot of the older folks, people who have to carry on with like they can barely finish their workout and they're just like sleep or tired.
Yeah, so what they are, with people with emphysema, remember, even though they're on supplemental oxygen, it's still lower than what it should be, and the carbon dioxide is higher than what it should be for those individuals, even though the kidneys are helping them to compensate. And so part of their problem is that they have lost actual functional lung tissue. They have literally gone in and, you know, poking holes into your lung tissue like Swiss cheese is not a good way for you to actually have all the oxygen transfer that you actually need. So that's one reason why their oxygen levels are so low, is because they've literally lost functional respiratory membrane. And they have to, even though you don't see them, they have to work so hard. That's why COPDers have to work so hard just to ventilate. So when you are working hard to breathe, it really consumes up a lot of energy, and so you don't have a lot of reserves left over to actually help you to do any sort of real active physical therapy. So that has a lot to do with it. Yeah. Yes?
So just going back to the point you made about how if you increase the oxygen, then it decreases their own personal.
Respiratory drive.
So with patients who don't have the right idea about what the oxygen is for and turn it up because they feel like they can't breathe, turn up their own oxygen, that's actually making it harder for them to breathe.
Typically, home oxygen delivery is not going to go really very high. So you know, if they're in the hospital because they're hooked up to different kind of tank mechanisms, they can really up their level. But most home oxygen delivery systems are not actually going to be able to really up their oxygen
Well,
delivery.
I work
to
in a
them.
facility where, I mean, there's like it's like, it goes up to like 6, it's like 6 meters.
6 liters per minute, yeah.
And when they're supposed to be on 2,
Mhm.
it's a large difference.
And if the person is feeling like they need more oxygen, they're actually a better gauge of what's going on.
Mhm.
But as long as they don't start to hypoventilate, they'll be okay. But if they start, their respiratory rate starts to drop, then they're actually putting themselves into more of an acidotic situation with it. So it's, emphysema, end-stage lung disease is a bad thing to have. I mean, there's no fixing it without a lung transplant for that type of stuff. Yeah. So, the other thing too, what's also very interesting is, I don't know if you guys know, but Navy SEALs obviously have to do quite a bit of diving. And they actually test them on a regular basis with PO2s of around 60%. So they'll put them underwater diving, doing various drills, and they'll make them drop their PO2s to 60, which they found is about time to actually up the O2 content for the individuals in order to actually function properly.
Half of what you need.
Yeah, so it's pretty crazy. All right, we'll stop there and do